Okay, so okay, let's get started. Okay, so last class we talked about the sensitivity conjecture. And we kind of finished our segment on spectral graph theory, and we started a new topic, which was the sunflower lemma. Okay. In some sense, we defined the basic sunflower set, the combination, and also looked at the Erdős-Rado theorem. Okay. So today, what I'm going to do is kind of revisit this proof. We sort of rushed at the very end, but that's the simplest way to look at it. If you just wanted to prove that theorem, that's what you would do. But now I also want to kind of generalize it a little bit. So we'll do another version, slightly different version of the same proof. And so statement of sunflower conjecture and where we are headed. And the new sunflower lemma proof. Okay, so that's where that's the goal for today. And so just to recall, if we had a collection of sets F, let's call them S1 through Sn, and actually, let's not do it this way. Okay, so there is some set C such that all of the pairwise intersections are exactly that set. In fact, they all have to be equal. That's the main constraint. Okay, so if your sets are disjoint, it's a sunflower. If they just contain exactly one element, it's a sunflower, and so on. Okay, so equivalently, you can also say this is also helpful to think about. If you let C be the common intersection of all of the sets, then once I remove this common intersection, there's nothing left in the intersection. Okay. So this is equivalent to the sets S1 through SR forming a sunflower. Once I remove the core, the sets become disjoint. Okay. And you can get to the core by saying it's a common intersection. All right. And then we saw the statement of the Erdős-Rado sunflower lemma. Right. So Erdős-Rado. Sunflower lemma. And what did it say? So if you had any collection of sets which are, you have some number of them, all, we don't care the size of the universe, okay? But each set is of size at most some k, okay? If the number of sets is bigger than k factorial, there exists a sunflower in F with R sets. Okay, so the two parameters that we're mostly interested in, how big the sets are and how big a sunflower do we want are, okay? And we want to say that, once your set family becomes big enough in terms of the number of sets, you will get a sunflower of size R. So for example, let's take R equals 3, okay? If R equals 2, there's nothing really to prove. I mean, it's just two sets, right? Sunflower is a trivial thing. But if R equals 3, what does Erdes-Schroeder bound say? It says that as long as my number of sets is 2 to the k times k factorial, we get a 3 sunflower. Okay, 3 sunflower is just collection of 3 sets, right? Which look like this. This is my first set. This is my second set. And my third set should be this. Okay. As long as I have any collection of sets, which is more than 2 to the k times k factorial, I am going to find 3 sets which look exactly like this. All right. And so we saw a proof of this by induction. We'll go back to the proof in a little bit. But let's see what are the limits of this? We are getting 2 to the k times k factorial, but what should we expect the answer to actually be? Okay. Or let's think of it the other way. If I ask you to design a family of sets of size at least k and do not contain a sunflower, what is the best you can do? Like, what's the worst family? Okay. So example. How tight is Erdes-Schroeder? Okay. Can we come up with examples which are better? Any suggestions? Think of some family which might give us some hint. Okay, but that's only one set, right? We need all the n+1 elements. So let's see. So the first idea is U is 1 through 2n, and F is all subsets of U. Size of S is n+1. Okay, so a good suggestion. So let's see if there is a sunflower here. Okay, so if you want a sunflower, then you want 3 sets, S1, S2, and right. There may be a sunflower here actually, right? Because let's say I take, yeah, in fact, there is a big sunflower because I can take sets of the form. Let's say C is 1 through N. Okay. And S1 is C union N plus 1. S2 is C union N plus 2. And N is C union 2N. Okay. So all of this collection of sets forms a sunflower and they're part of the family, right? So we do get a big sunflower from this collection. Okay. So how can we avoid a 3 sunflower? And remember, one thing we're trying to do is to limit the size of the set. Okay. We are allowed to pick the universe as big as possible, but the size of the set should be at most K, and we're trying to parameterize in terms of K. Okay. Excuse me. Thank you. So how can we find a family? And there is a clever construction. It's kind of non-trivial to come up with, but there is a clever construction which gets which is still the best known. Okay, it's been known for a long, long time. And I should say that this was proved in 1962, right? And what is this clever construction? All right. So I'm going to write down or pair up elements. Okay. So I have 1, 2, 3, 4, 5, 6, so on. There are K rows, and I'm just paired them up into 1, 2, 3, 4, 5, 6, so on. Okay. Yeah. Sure, I'll do it later. Yeah. Okay. So you have 1, 2, 3, 4, 5, 6, so on up to 2K minus 1 and 2K. Okay. And now you have K rows. We need to pick this set. I'm going to get a family of sets out of this K rows so that you don't get a sunflower. Any guesses on what that might be? So we're trying to avoid a sunflower, right? And we need sets of size K. Any guesses? So the clever thing is to, if I want to pick 3 sets which have a common core, well, anyway, so let me tell you the answer because it's a little bit kind of, you need to think about it and somehow it has to click. So the family of sets is follows. I'm going to pick a set family where every set has 1 element from each row. Okay. So F equals all sets S of size K that contain 1 element from each row. Okay. So I'm either picking something like, I can pick one, either this is one set, or it could be 1, 4, 5, and so on, 1, 4, 6, so on and so forth. Okay. So how many sets will be there in this family? Every row I have 2 options. So it'll be 2 to the K, right? Because I can pick 1 or 2 for the first one. I have 3 or 4 for this next one, and 5 or 6 for the next one, and so on. Okay, so it's a big family. So size of the family is 2 to the k, right? And each set has exactly k elements, right? Okay, so for example, if k equals 2, then f is essentially, so I can do 1 comma 3, 1 comma 4, 2 comma 3, 2 comma 4. Okay. And my claim is that this family does not contain a 3 sunflower. Why is that? Claim F does not contain a 3 sunflower. Okay, so proof. Well, intuitively, if I have 3 sets S1 to S3, take any row, okay, one particular row. If they intersect in some element, that means that S1 and S2, so let's say I have these 2 things. Okay, this is one set, this is one set. Either they're disjoint or they have some overlap, okay? But if they intersect, that means that on some row, S1 and S2 contain the same element, but then S3 must also contain the same element, right? And, okay, so let's see. Suppose S1, comma S2, comma S3 belong to F and form a sunflower. Okay. My claim is that this is not possible. Why is that? Let C equal the common core. Okay. And whatever is in the common intersection will pick out some rows. Maybe it picked out, let's say, this row, this row, this row. So you had some element here, some element here, this element here. All of these are part of S1, S2, and S3, all 3 sets. Now, what should happen in the remaining rows? Once I take out the core, the sets must be so they form a sunflower if and only if this happens. R is joint. Right? Okay. But can I have 3 sets which are actually disjoint from my family? Yes or no? Can I pick 3 sets which are disjoint in this family? No, right? Because for each row, there are only 2 options. So either the first one contains 3, then the second one contains 4, but the third one has to contain 3 or 4. There are only 2 options and have 3 sets, so they must overlap. Okay? And this is not possible. Okay? So we're exploiting the fact that in each row, I only have 2 options, but if I have 3 sets, then they must have something in common. Okay? Any questions? All right. Okay. So now, so this is a family which is of size 2 to the k and does not contain a sunflower. And as it turns out, this is the best construction that we actually know. Okay, to date, this is the best family that we know. And a conjecture that's been open for a long time. Okay. So we know that there is a family of size at least 2 to the k, which contains a sunflower. And the Erdy-Schreiber thing says that 2 to the k times k factorial will guarantee a 3 sunflower. And we don't know where the answer lies in between. The conjecture is that there should be some exponential factor which suffices to guarantee a 3 sunflower. Okay. That's for the case of finding a 3 sunflower. Now, how about a R sunflower? Let's say I want to extend this example to avoid sunflowers, like R sunflowers, not just a 3 sunflower, meaning sunflower with 3 sets, but sunflower with R sets. I want to make the family of sets bigger now. How can I build some family which is similar to this? Any suggestions? I want a bigger family, but you're allowed to now, you only have to avoid bigger sunflowers, like R sunflowers, where let's say R is 4 or something. Yes, exactly, right? So you can just use the same idea, but use R minus 1 columns. I mean, I drew it as a square matrix, but it doesn't really have to be. So R plus 1. Okay. And F is all sets that contain exactly one element from each row. Okay. So once again, if I have R sets, basically, in each column, I only have R minus 1 options. I cannot have them be disjoint. And if some 2 are not disjoint, all of them have to be not disjoint. Okay, so that's how you're winning. Because there are only R minus 1 options, some 2 must overlap. But once some 2 overlap, all of them must contain that element. Okay. And what is the size of this family? So just like before, we have R minus 1 to the power k. Okay. All right. Okay. So, and here C is supposed to be any constant. The conjecture is for any constant. It could be 2 or it could be something else. All right. Okay. So in summary, so what do we know? Let n of R comma k be the smallest n such that any family that contains n sets. Actually, maybe let me say be the largest that does not contain a R sunflower. Okay. Suppose I ask you to pick the largest possible family in terms of the number of sets. Each set is of size at most k. I don't care the size of the universe. You're allowed to pick whatever universe size that you want, but you should not contain an R sunflower, meaning a sunflower with R sets. Okay. So what did we just see? There is a family. So what do we know? So we know that R minus 1 to the k is at most n of R comma k. Okay, this is by construction. Right, so this example 2 shows that there is a family of size R minus 1 to the k and does not contain a sunflower. Okay, so F does not contain a R sunflower. Okay, and also by Erdős-Rado theorem, we know that this is at most R minus 1 to the k times k factorial. Okay, so there was this huge gap by a factor of k factorial between these two. Okay, and this stood as just like this for 60 years. There was no improvement, some minor improvements, some various reductions and so on, but nothing really changed in this picture until 2020. Okay, so what happened in 2020? Let me pull up the exact bound. Yeah, okay. So in 2020, there was this really remarkable breakthrough. And historically, in some sense, this was this was always just a problem in combinatorics, which had applications in theoretical computer science. Okay, so people use this to prove communication complexity lower bounds, to prove circuit lower bounds, to prove data structure lower bounds, to get algorithms. I used it to get an algorithm in one of my papers in during my PhD thesis and so on. Okay, but there was nothing like towards improving the bounds from computer science. Okay, but then in 2020, there was this remarkable paper by Ryan Alewies, Shahar Lovett, Kevin Wu, and Jiepeng Zhang. And they showed that really n of R comma k in our current notation is at most some constant c times okay. So one one way to compare these two things is there exists a constant c. I mean, constant is not that bad, but it's not important, such that this holds. Okay. Now, one way to compare these two bounds is to this is essentially like R minus 1 to the k times k to the k. So how does k factorial grow with k? It grows as k to the k up to some constant, like k over e to the k or something like that. Okay, it doesn't matter. So instead of getting k to the k, now you have log k to the k. Okay. So for instance, this tells us that n of 3 comma k is basically some constant times log k to the power k. So it's getting very close to the conjecture. Okay. You know, instead of getting c to the k, you're getting c log k to the k, whereas the previous one was k to the k. Okay. All right. And I should say that in the same paper that define the sunflower lemma, and this is the sunflower conjecture, that for every r, there exists a constant CR such that okay, so this is the conjecture. That for every r, there exists some constant such that as long as I have exponentially many sets, you will find a sunflower of size r. Okay, this is open even for r equals 3, but this paper made a lot of progress towards proving this conjecture, improving the known bounds significantly. Like, you know, we were stuck at this essentially for like 60 years, and then there was this dramatic improvement. Okay, and that's what we're going to talk about in today's lecture and the next lecture. And along with the statement, which is itself very interesting, we will kind of explore two important ideas. Okay, one is in terms of how to use probabilistic arguments to prove combinatorial or deterministic statements. So if you look at the sunflower, you know, the statement, the sunflower theorem, and so on, there's nothing about probabilities here, right? There's no probability, there's nothing here, but these things will show up. Okay, so that's the first idea, that, you know, it's a meta idea that transcends this application and kind of shows up everywhere, something I've used in my research a lot. And maybe if time persists, you know, time allows, time permits, we'll get to it again in the last topic. Okay, so that's idea number one, using probabilistic arguments to prove this stuff, especially in some kind of dichotomy. The second one is to use compression to compute probabilities. Okay, so these are the two main ideas. There's this concrete application, but the two main ideas are using probabilistic arguments and then using compression to compute probabilities. Okay, the second one is particularly novel for this application. That's actually comes from circuit lower bounds. Okay, yeah. So the question is n of 3 comma k, that's exactly corresponds to r equals 3. Okay, any questions so far? All right. So with that set aside, so let me say, you know, remark two big ideas. One, okay. There's a question. It was Zoom. Yes, you know, we are basically ignoring constants. So yeah. Okay, anyway. All right. So for the first one, you know, this is something, again, you should always keep in mind when you're dealing with questions in theoretical computer science and so on, especially in algorithms, right? Sometimes you're trying to solve a problem, but it helps to make the problem harder counterintuitively, okay? The reason that helps is, you know, when you're, let's say you're trying to, you know, write some program or something, sometimes it helps to add extra functionality than what you need, because you might use it in some inductive way or recursive way. Okay, you know, you're trying to build a class, you add extra functionality so that you can maintain something for future use, right? And that's what's going to happen in here too. Okay, all right. Okay, so with that said, let's go back to the original proof that Erdős and Rado had in 1962. Let's see if we can tweak it somehow. There was kind of an elementary inductive argument, clever, but we did not use any heavy tools, no probability, nothing like that, right? So let's go back to it and see if there are some, tricks that we missed to make the bound better. Okay. Obviously, people had, many people tried to do that for 60 years, nothing happened, but let's still go back and see if there are some tricks that we missed or something else we can do with that. Okay, so let's revisit that argument. Erdős and Rado in 1962. Or in other words, if I have a family with size at least r minus 1 to the k times k factorial, then we get a sunflower. Okay. So the argument was based on induction. So alternately, if f okay, so whenever I write a family, just understand that it only contains sets of size at most k. Those are the only sets that we're looking at for now. So let's just stick to that, right? So f has sets of size greater than or equal to, sorry, less than or equal to. Okay. And the way we proceeded was to say, find a maximally disjoint collection of sets, S1, S2, so on, in F. Okay. Keep picking disjoint sets. At some point, you have to stop. If L is bigger than R, or at least R, then you're done. Okay, you have disjoint collection of sets, so they form a R sunflower. If L is greater than or equal to R, we found a sunflower. Right? I'm just rewriting the same thing from last time, but we're going to change or try to make it better. If L is less than R, then we said, look at this. Okay? And we said there exists I in I such that if you define Fi equals okay, so this was the argument. We said, if L is less than R, then there exists an element such that if I look at all sets which contain the element I, and they take out the element I from them, then the size of this family is still somewhat big. I started out with some F. Now I have a reasonably big family, but the win is that this family is of size, only contains sets of size k minus 1. Okay. So now we could use induction on this, right? Makes sense? So that was the argument. So in some sense, we said, so which is bigger than or equal to r minus 1 to the k times k factorial divided by r minus 1 times k, which is, again, we could use induction, right? So if this is true, Fi only contains sets of size k minus 1, and its size fits the same formula. So it must contain R sunflower, and hence F itself should contain R sunflower. Okay. That's the argument. Now, how, so that's the basic inductive argument, right? Is there any way that we can potentially make it stronger? Like what we did here was identify one element and said, look at all the things which contain this one element. If I take it out, I'm reducing the size of the family by 1, reducing the size of the sets in the family by 1. I just need to use induction on k minus 1 now. Okay. So this gave us this bound, kind of, you can't do much better than this. But is there anything else that I can do which is similar? Let's say I want to improve this bound. What are stuff I can try? Any suggestions? Like, we got, let's say, okay, let me give a hint. Maybe, what if I found a pair of elements? We call them I comma j, such that so here, essentially what we did was we took out one element, okay? And we hit the inductive bound for k minus 1. But it's okay if I take out 2 elements too, potentially. But what should I shoot for here? How big a family should I need? So for example, would this have also been enough? Suppose I found 2 elements such that taking them out and looking at all sets which contain them, I have a subfamily now, which is still sufficiently big. I can still use induction, right? Because it's the same kind of bound. So when I'm trying to use induction, it's this bound. It's R minus 1 to the k times k factorial, right? If you're looking at sets, a family where the sets are of size k, then you should look for that. Otherwise, if I'm looking for a family of sets of size at most k minus 1, it should be R minus 1 to the k minus 1 times k minus 1 factorial, and so on. Okay? So there's nothing really wholly or particular about only trying to induct from k to k minus 1. I can induct from k to k minus 2, k minus 3, or maybe all the way. It doesn't matter, right? As long as I make some improvement, I can try and use induction. Okay. So this is exactly what we are going to do, right? So even then, we can use induction. Okay, so instead of taking one element out, I can try and be greedy and say, can take whatever size elements that you want, but after that, I need to find a family which is still somewhat big. Okay. So that's the first idea. Idea 1. Okay, so let's rephrase this argument, maybe. So Eddy-Schroeder argument can be thought of as 2 steps. Okay. So maybe first let me define a definition. For a set family F and an element A, FA is all sets in the family which contain the element A, and then you take out the element A. Okay, look at all sets which contain the element A, and then you take out the element. Okay, so now you have only k minus 1 elements if you had k elements before. Okay, so the Erdes-Shadow idea is if there exists an element A such that FA is bigger than or equal to we are done by induction. Okay, I'm just rewriting in a slightly more formal way. So there's like a case analysis. If there exists an element such that the link, the set FA is big, then we're done by induction. Otherwise, we have to do something, right? On the contrary, if for all elements A, size of FA is strictly smaller than this, then F contains R disjoint sets. Okay. So this is the template for Erdes-Shadow's thing. And of course, here there's nothing special about a single element A, right? Maybe if I try to pick out 2 elements, I can do better. Maybe 3 elements, I can do better, and so on. Okay. So one first attempt could be something like this. I'm going to follow the same template. And for, there are good intuitive reasons, but even without that, you might wonder, given that this gave us such a bound, one might try to improve by trying to find bigger sets to take out. Okay. Instead of taking a single element, I'm now going to look at potentially any set, maybe pairs, triples, and so on. And what should I define here? What would be the analogous set to look at? Analogous set family to look at? Fi should be just like exact analogy to what we were doing with the single element. I want to do it for maybe a pair of elements. So what should I do for that? Right, so look at what we were saying here, right? If I have a pair, I have to look at all things which contain the pair of elements and remove it. Okay. In the same way, I can go back here and say, okay, look at all sets in my family which contain the set I, and then I take out the set I from them. Okay. I might have made the size of the family smaller by doing this, right? Because I'm now imposing this constraint that the set I must be contained in your set. So I'm going to a smaller family of sets. But what is the win? What do we gain by doing this? So the win is that the size of the sets has become smaller. Okay. So how can I rephrase this? If there exists a set I such that what should I put here? Size of I, right? Because, you know, in some sense, everything in Fi is of size at most k minus size of I. Okay, so I can use induction as long as this holds. Okay, and then the contrapositive that I need is this. Okay, so even if I could do this, I could have done the induction argument. All right, any questions about this? So instead of taking out one element as we did in the Erdish-Rada argument, we're going to try and use induction where I'm going to pick out more elements at a time. Okay, and this set Fi is called the link of I in F. Right? Okay. And to get the best bound, so what ALWZ20 did, more or less, is the following. They said, we'll follow the same template that we are shooting for. Okay. And we're going to use induction where something like this happens. I don't know what, I mean, I'm trying to improve the Erdish-Rada bound. So I'm going to try and find some function, maybe something better than what they had for which this holds. And I need to show this condition. Okay. So if such a thing is true, then once again, by induction, I would get, so this would imply by induction, okay. All right. So this is what we're going to do. We're going to find a suitable function such that we can do this induction a bit more efficiently. All right. I mean, in some sense, given that this proof of Erdish-Rada was around for 60 years, it's kind of surprising that nobody thought, okay, instead of taking out one element, we should try and take two elements or three elements and so on. But that's a simple conceptual step, which does help. Okay. But even after that, you need to do a lot more stuff, but we'll get to that slowly. Okay. So let's take a 5-minute break. And when we come back, we will focus on this exact, like step 2 is where the hard stuff is, more or less. Like the first step is just induction, right? If there exists a set I such that that is true, you're done by induction. There's nothing to prove really. But when you cannot make that progress, that's when you have to show this, and that's where the heart of the proof is. Okay. Even in Erdish-Rada's classical argument, that's where we basically said, if none of the elements is contained in many things, then by some kind of averaging, you must contain R disjoint sets. Okay. So step 2 is where the complicated things are, and that's what we're going to focus on. Yeah. Oh, sorry, for every set, for every set. Yes, yes, yes. That's a good point. This should be for every set. That's very important. Okay. In fact, we are not even going to like limit the size of the set I. We're going to say all sets of size 1, we're not able to make progress. All sets of size 2, we're not able to make progress. All sets of size 3, we're not able to make progress, and so on. So we're going to assume that none of these things, none of the inductive things were possible. So it's a very strong hypothesis to start with. Okay. So we kind of strengthen the hypothesis. For every I, we have this condition, but then we have to end with this R disjoint sets. Okay. Yeah, this should also be there. Okay. So we are really going to use the fact that this condition 2, you have this for every I. Right? Okay. All right. So let's take a 5-minute break. And when we come back, we'll get to this thing. And that's where probability will enter. All right. And yeah, sometimes, one of the big steps in making progress on such long-standing questions is to come up with the right definition, that gets you started. And here, I feel like this definition itself is really, really useful. And as it turns out, and another symptom of that is different people come with a definition in different languages, and you don't know about it. Okay. And this is a notion that we're going to talk about, which is directly modeled after what we're asking for here, right? So the hypothesis here is somehow saying you have your set family F, and you look at the links, which are basically subsets which contain a specific set I. None of them are too big. That's the hypothesis. Okay, so that's kind of so what is the hypothesis? For every I, there's some quantitative bound, but we want to say is small, right? Somehow compared to the size of the family, the size of the link is very small. Intuitively, this is saying that if you think of your sets, there is not a single like element which is contained in every one of them. If it was, you would take it out. If there's a pair of them which is contained in half of them, maybe take it out again, right? Somehow, every time you add an element, the size of the family should decrease appropriately. Okay. And there are various ways to quantify that, but somehow the simplest way is also what works. We'll say a set system F is S spread. Okay, is S spread if the following holds. First, the size of the family should be somewhat big, is at least S to the K. In some sense, what we're doing is going here and focusing on the exponent rather than the base. You can also bring the base into the thing, but let's first try and get the exponent right. Okay. So is S spread if the family is big to begin with, but then for every I, the size of the link is small compared to the size of the family. All right. How small? Every element you add should cost you a factor of S in the size of the family. Okay. So we'll say a set system is S spread or spread if for every I, if I insist on, okay, look at how many sets contain the number 1. then this number of such sets is 1 over S fraction of the total. How many sets contain the elements 1, 2? It should be 1 over S squared fraction. If I ask you to contain 3 elements, it should be 1 over S cube and so on. Okay. Insisting on every single element, adding one single constraint costs you a factor of 1 over S. Okay. Does this make intuitive sense about what the bound is saying? Yes, no. Okay. So, and it's called spreadness because it's essentially saying that the sets don't overlap too much. Okay. All right. So this, for example, okay, so every time I insist you need to contain this element, you lose a 1 over S fraction in the size of the family. Right? Okay. So that's the notion of spreadness. And the main theorem that was shown in this paper, LWZ20, and this notion of spreadness has found many applications since, is the following. The exact quantitative thing is not too important, so don't worry about that for the time being. Okay. Okay. So saying if you have a spread family with some spreadness, then it must contain our disjoint sets. And this bound has since been improved. We'll talk about that later on, but let's just understand the exact sort of formulation here. Okay. Any questions about the statement? No, fine. Okay. All right. So in comparison, the Erdős-Rado statement, the proof, maybe it's R minus 1K really. Okay. In terms of the spreadness required to guarantee that you have R disjoint sets, the old proof had something like R minus 1 times K. And that's what went into the inductive argument, like R minus 1 times to the K, and then R minus 1, K minus 1, and so on, right? So here, it's like this log. So you have almost an exponential savings in how much spreadness is required to guarantee that you find disjoint sets. Okay. And what I want to do today is just, well, I guess, let me call this the main spreadness lemma. Okay, so the main spreadness lemma implies the, where did that go? Okay. Misstated it somewhere. Yeah, this bound. Okay, so the main spreadness lemma implies this. That basically follows from induction. Okay, you just have to work through the induction a bit carefully. It's a little bit tedious, but the proof is just saying okay, you start with a family which is this big. Okay. Suppose I have a family which is this big. Then you consider case one. There exists a I such that size of fi is bigger than or equal to let me just write it as s to the minus I times size of f. Okay. If this is true, we are done by induction. Okay. Case two, for all I, you have this implies f contains R disjoint sets by the spreadness lemma. Okay, I'm just writing down the inductive step. If this is what we wanted to prove, the significant improvement in the main sunflower bound, and we're just saying, if your family is big, then either there is an I such that you can use induction, or otherwise you have a spread family and you would get R disjoint sets. Okay, so the entire thing is in proving this statement now. When you cannot use induction, we want to say you're done because you can find disjoint sets. Okay, so that's what we're going to focus on for today's lecture and the next lecture. All right. So how do we get to that bound? And here's again like a slightly, it's kind of a leap. So it's hard to motivate it, but I'll try and do it in some way. It's kind of a leap in the sense that because we're trying to prove this lemma that if you have a spread family where spreadness is something like this, then you contain R disjoint sets. Okay. So one intuition to keep in mind is somehow, and it's very vague intuition, is sort of draw two mental pictures of a family of sets which is spread and a family of sets which is not spread. Okay. So let's say I want to draw some sort of caricature of a spread family versus a non-spread family. How would a spread family look like? What kind of, shows up in your mind when I say, okay, think of a spread family of sets? How do you picture them looking? Or think of one example of spread family. Somehow spread means that the sets are actually spread out over the universe. It's literally in the word, because somehow no element is contained in too many of them. Okay. So for instance, this would be a spread family. Like if I have this, something like this, maybe they have some overlap, but not like too many things. Right? This is kind of a spread family because let's say I consider this element and I say, look at all sets which contain this element, there are not that many of them. Okay, no single element is present in a large fraction of the sets. No pair of elements are present in a large fraction of sets and so on. Okay, whereas something like this would not be spread. Okay, the colors are bad, but you get the picture. So this is spread. This is not spread. Right? This is not spread because somehow all of these sets have a common intersection. And if I look at the link corresponding to the intersection here, I have many, many sets than what I should. Okay. So that's the picture to keep in mind. Spread means the sets are kind of all over the place. No single element is present in many of them. Okay. And one big leap or sort of a magical thing, in addition to going to spread families, which is somewhat natural because you're trying to extend the induction and Erdős-Rada argument. But the other sort of much more non-trivial conceptual leap that they took was to look at the following. Okay. They said, suppose I have F, which is S spread, where S is some bound, like whatever we had earlier. Right? Now we are trying to find R disjoint sets. Like for instance, maybe let's say this set is disjoint. Okay, let's say this one, this one, this one, this one, this one. Right? Given a spread family, we are trying to identify disjoint sets. So how can we find these disjoint sets? Kind of somehow we need a filter which will pick out these disjoint sets, right? And a sort of a weird thing they came up with was the following. Suppose I pick W is a random subset of the universe U okay? And they said, I'm going to pick a completely random subset of the universe U. And the random set is, again, I'm going to draw a caricature. So like I pick this is my set W. Okay. Maybe let me draw the most extreme non-spread set, which would be something like this. All the things are really focused kind of here. Right? They're all clustered. Instead, in the spread case, if I take a random set, then there should be some chance that I actually hit one of these sets. But if all of the sets are very clustered, then I should be unlikely to hit a set in the family. Okay, again, qualitatively, it makes sense. The fact that quantitatively you can get tight bounds is completely different. Okay, so does it make intuitive sense, the statement? Like I'm saying, when the sets are spread out and I pick a random set W, just imagine I throw a random square, the chance that it sort of hits or even contains one of these blue blobs should be higher in the left picture than in the right picture. Because in the right picture, all the blue things are concentrated. They're covering less of the universe. Okay? And that's exactly what they showed, that if I pick this set W, you can think of it as a witness at random, then with high probability, one of the sets in your family is completely contained in your witness set W. How high a probability? It's at least 1 minus 1 over 2R. Okay, this is called a robust sunflower lemma. Okay, and this is what I said, we are going to go to the language of probability at some point, and this is where it's happening. Okay, instead of looking for disjoint sets, I'm going to ask for something seemingly stronger or even maybe unrelated in some sense. I want to bound the probability that if I throw a random set like this W here, what's the chance that I contain something in the family? Qualitatively, it makes sense that this probability would be higher in the left picture than in the right picture. Okay, and turns out that is actually very true. In fact, for a spread family, the probability is quite high, 1 minus 1 over 2R. Does the statement make sense? As I said, this is again a conceptual leap, which is important. You're pulling a rabbit out of the hat by expecting such a statement to be true. Okay, there is some history behind it, some precursors in some hidden forms, but I think it's still a very nice leap. Okay, so this is a robust sunflower lemma that we will prove later on. But first, let's see that the robust sunflower lemma implies the main spreadness lemma. Okay, why is that? This should be somewhat mysterious. Let's unpack it. What is this saying, right? So the robust sunflower lemma says, I have a spread family of sets. I pick a random set W. I mean, it doesn't have to be contiguous. I drew it in a contiguous way. Then it contains one of the sets with probability 1 minus 1 over 2R. And I want to use this to say that there must be R disjoint sets. How can I do that? Okay. So the way they did it is the following. So what are we really trying to do, right? So let's say the universe U is 1 through, n, or maybe even little u, doesn't matter. Okay. So the robust sunflower lemma says we pick a random subset W1 of size U by R, then probability there exists S in the family such that S is contained in W1 is at least 1 minus 1 over 2. Okay. So what they suggested, I mean, the clever thing now is to use this to get R disjoint sets. Any ideas on how we can do that? Exactly. Exactly, right? So the idea is that somehow, one way to pick, there are different ways to pick these disjoint sets. And one clever way, as suggested here, is, just imagine I order the elements of the universe completely at random. Like U minus 1, maybe 1, maybe 17, so on. Okay, so order at random. Okay, and then I say the first 1 over R elements are W1. And then I take W2 to be the next U over R elements. Okay, W2. W3 is the next U over R elements. And so on. Okay, so I have picked, so we get W1, W2, all the way up to WR. Okay, so let's say R divides U, otherwise it's not a big issue. Okay, and what do we know? One, W1 through WR are all disjoint. They're not independent because you know that I'm picking this to be the first one and then the next one and so on. So they're definitely not independent, but each one by itself is a uniformly random set of size exactly U over R. Okay, so the distribution of this is the same as the distribution of this. As a distribution, not as individual elements, but as distribution, they have the same distribution. Okay, so in particular, each Wi is a random set of size U over R. Okay, so what does this mean? This means we have probability that exists S such that by applying the robust sunflower lemma to W1, W2, WR, they're all exactly the same distribution. So it's the same statement applied R times. Okay, you get this. So if you go back to this picture, what we are saying is, I chose this as my W1. Now I'm going to choose my W2, which is some other random set, maybe over here. Okay. It is definitely guaranteed to be disjoint from W1. Okay. And then I have W3, maybe it's something like this. Maybe I have W4. And so on. Okay. So I partition the whole thing into R disjoint groups. Each one is exactly of size 1 over R of the whole universe. And with high probability, each one contains one of the sets in the family. Okay. If all of them happen, then I'm good, because if I look at S1 be the one which is contained in there, S2 is the one contained in here, S3 is the one contained in here, and so on, they must be disjoint because W1, W2, W3 are disjoint. Okay. So if all of this happens simultaneously, then I'm happy, right? So each one has a high probability of happening, but we need to argue that somehow there's a high chance that all of them happen simultaneously. Okay. How can I argue that? So, as an example, suppose, I tell you probability I win lottery is 0.9 for whatever reason. Probability you win lottery is at least 0.9. Okay. And this need not be independent. Who knows, maybe our numbers are correlated and so on. But what's the chance that both win the lottery? Can I get any lower bound, and what's it on the chance that both of us win the lottery? What do you think? So I have a 90% success rate. You have a 90% success rate. What's the chance that both of us succeed without knowing anything about, dependence, independence, or anything? My claim is we can still get a pretty good lower bound on the chance that both of us win the lottery. What can we say about that? So someone in the Zoom actually mentioned we should be using the union bound on the complements. So meaning here, the chance that both of us win the lottery is actually, what do you think? How high do you think it is? Is it low or small? Just take a guess. How many of you, you think it's low or small? Well, it's actually very high. It's at least 0.8. Right? And the reason is that if you look at the complements, it gets better. Probability I don't win the lottery is only 0.1. Probability you don't win the lottery is at most 0.1. So probability neither, at least one of us doesn't win is at most 0.1 plus 0.1, which is 0.2. Okay, so this is the union bound. So in some sense, even when the events are not independent, we can get control on joint probabilities if the beginning probabilities are very high. Okay, if you have 10 events, each one has a 99% chance of succeeding, then the chance that all of them succeed is 90%. Okay, so that's what we're going to use. In particular, you go back here and say probability there exists no set in the family, of course. Right, I'm looking at the complement of this statement. Probability there exists no set in the family which is contained in the first witness W1 is 1 over 2R. And similarly, 2 is this much. Okay. And just for clarity, let me put this numbering here. Those are just variables, it doesn't matter, but let me just add a number to make the notation clearer. Okay. So some bad events, if there is no set for the first witness, that's one bad event. I have another bad event, and so on. But each bad event is extremely unlikely, and the number of bad events is only R, right? So altogether implies probability for some okay. So if I have various events, the probability that at least one of them happens is at most the sum of the individual probabilities. Okay, this is called the union bound. If I have events E1, E2, all the way up to ER, then the probability that at least one of them happens is at most the sum of the individual probabilities. Okay. So it's like saying, if the chance of rain is 0.1, and if the chance of, let's say, sun is 0.1, the chance that both of them happen is at most 0.2, or one of them happens at most 0.2. Okay. All right. So what do we gain from this? We gain the following. So this implies that probability for every L there exists a set SL. Okay, so I'm just taking the complement. So the chance that there is some L which does not contain a set in the family is at most a half. So the chance that every WL contains a set in the family is overall a half. Okay, which is in fact greater than 0, right? So this in particular implies that there exist R disjoint sets. It's actually giving you kind of a semi-algorithm to find the R disjoint sets, saying pick this W1, W2, WR as before, and each one of them with probability half, every one of them will contain a set. So high probability half, every one of them will contain a set. But because these W's are disjoint, by definition, the internal sets must also be disjoint. So we have R disjoint sets. Okay. Again, as I said, this is almost like an overkill to shoot for such a thing. when we only want to find R disjoint sets, but this is true. And shooting for such strong statement actually helps kind of get a more sophisticated induction to go through. All right. So let me stop here. In the next lecture, when we come back, we will focus explicitly just on this robust sunflower lemma. All right. Okay. So I'll see you all on Monday.